recording. Okay, so the last thing we talked about was this proposition that the covariance matrices are positive semi-definite. So I'm not going to repeat that, but just as something that is good to remember. So one last thing that we want to talk about before we move on from this chapter or this topic is this idea of decorrelation or whitening. And so this is going to be interesting, but we're not going to use it as much in this course. So I'm going to briefly mention it, and we'll come back to it at some other point. So suppose you have a random vector y, and the idea is that we would like to find a linear combination of the elements of y such that the resulting vector has covariance identity. So this I can do by taking a linear transform A and forming this A times y. So if you think what A times y does, each coordinate of z is going to be a linear combination of the coordinates of y. So each coordinate of z is a linear combination of the coordinates of the coordinates of y. And sorry. Okay, I'll do that later. So I would like to find A such that this resulting vector has covariance identity. So another way of writing it is this. So identity has diagonals that are all 1 and the off-diagonal elements that are 0. So why would this be interesting? Because then the components of Z will be uncorrelated. And then they would have unit variance because the diagonal elements of the covariance matrix are variance. So they would be both uncorrelated and unit variance. And so this is a form of standardization, which is a form of standardization, which is going to be generally useful. It's like taking the mean off and then dividing by the standard deviation. The usual way that you standardize a random variable. This is like the vector matrix version. So how do we get A? So here is the simple solution. So A would be the square root of sigma inverse. So this is going to be equal to, you can think of it as the square root inverse, which is also going to be equal to the inverse square root. So they're all the same. So you can write it the way I wrote it without confusion. So this notation means either of the two, and the two are the same. So anyone remembers what the square root of a matrix was? Can anyone tell me what the square root was? So sigma here is the covariance of y. What does it mean to write sigma to the 1/2?
It's the matrix where sigma to the 1/2 times itself is equal to sigma.
Can you say it again?
It's the matrix when multiplied to itself that is equal to sigma.
Right, that's correct. So, sorry. Sigma 1/2 times sigma 1/2 would be sigma, right? And so this is just taking the inverse of that. So what matrices have a square root? Do all matrices have a square root?
Positive semi-definite matrices do.
Right. So is sigma positive semi-definite?
Yes.
Yes, because we just showed that last time. So this is valid because sigma is positive semi-definite. It has a square root. And in addition, I'm assuming that, so in addition, so implicitly assume that sigma is invertible or non-singular, which means that it's a strictly positive definite. So no eigenvalue is 0. Then I can invert this square root. Then sigma 1/2 is also invertible. You can verify this for yourself because this is, if you remember, anyone remembers a formula for sigma 1/2? How do you compute sigma 1/2?
You take the spectral decomposition of sigma, and then you take the square root of the lambda matrix.
Yeah, yes, that's a good way of doing it. And that shows you that basically the eigenvalues of sigma 1/2 are the square roots of the eigenvalues of sigma. So if none of the eigenvalues of sigma are 0, then none of the eigenvalues of sigma 1/2 are 0. So sigma 1/2 is also going to be invertible. So the thing that I wrote here is valid. So I can make the inverse, or I can take the inverse. So let's see if this works. So if I have taken A to be this, then I know that from the formula that we did last time that covariance of Z would be just equal to A times covariance of Y, A transpose. And so A is just sigma negative 1/2. And I need to put A transpose on the other side. What is the sigma minus 1/2 transpose? Is sigma 1/2 symmetric, let's say, or not?
It is symmetric?
Yes. I'm not going to ask you why because, yeah, you probably know. If you go back, the way we define it is that this is the symmetric square root. There are other ways of defining a square root, but there is a unique symmetric one. So by definition, this is symmetric. And so the inverse is going to be also symmetric. So I don't have to put a transpose here. Sigma negative 1/2 is symmetric, so it's equal to its transpose. So I have that. Then I plug in covariance of Y, which is just sigma. And here's the trick. So I write sigma as sigma 1/2 times sigma 1/2. Okay? Because sigma 1/2 times sigma 1/2 is sigma, I just replace that. I just replace sigma with this. And you can see, I don't need parentheses in matrix multiplication. I'll just evaluate this first on this side. I'm going to evaluate this, which is going to evaluate to identity because these matrices are inverse to each other, and this is also going to evaluate to identity. So the result is going to be identity. And this is exactly what we were after. Okay, so this matrix works, and this Z is going to be like has covariance identity, or the coordinates are uncorrelated, that the variances are 1. So any question? No questions? Okay, just remember this. We'll come back to this. And as an exercise, there's another way of doing it. So you don't have to take A to be this. You could have, I believe I corrected this, someone in previous years pointed out, it might still be incorrect, but check that for yourself. You can take A to be this, which is not a symmetric matrix, but if U lambda U transpose is the spectral decomposition or the eigenvalue decomposition of sigma, then that is another choice. So A is not unique eigenvalue decomposition. EVD is eigenvalue decomposition, equivalent to a spectral decomposition. Okay, no questions? Okay, so let's move on then. So this is what I wanted to talk about in terms of the random variables and random matrices. We're going to use these results throughout the course. So we're going to revisit these ideas. What I want to move on now to is the idea of a multivariate normal distribution. Okay, so let me try to see if I can make a poll here. I wish I had made it before, but I would like to ask you guys to okay. Let's see if I can submit that. No. Oh. Okay, doesn't work. Sorry. Okay. Another try. Okay, doesn't work. So, how, just answer in chat. How many know about multivariate normal distribution? The multivariate normal distribution. If you know it, say yes. Otherwise, no. Kind of. Okay. Yes. No. No. Kind of. Okay. No. No. Definitely need to review. Not really. More people. Come on. No. Do you know or no? You don't know. No. Okay. So you don't want to. Okay. No. Another one. Okay. So what one of you that said kind of, do you want to share what your thoughts on are on it, or what is the kind of part that you remember? Herman, maybe you want to go? Herman or Harman, I don't know. Do you want to take a stab at it? You don't? Just one of you say something about, you could say something about the usual normal distribution. I hope people know about the normal distribution. Can you tell us anything about the normal distribution? How do you define a normal distribution? Just the univariate normal distribution. I'm gonna wait for you guys to come on and then talk.
But normal distribution, we can say, is the normal that the shape is bell, and we know about the mean and variance, and also about the the Chevalier function f of x is 1 over the square root. I say or no?
Yes, you mean the PDF. Yeah, probability density function.
Yeah.
Right. Okay, so mu and sigma. So let's say all distributions have mean and variance. So that's not anything related to necessarily a normal distribution. So if you want to define a normal distribution, it's a certain probability distribution. Okay. I would like to maybe spend a few minutes because most people usually are confused about what a distribution. So anyone knows what a distribution is in general? What is a probability distribution? What is a probability distribution? So a normal distribution is one kind of a probability distribution. So how do you define a probability distribution?
Isn't it just like some function that defines like the probability of an event occurring such that it's like less than or equal to a certain number, n?
Right, okay, so yeah, so in general, let's say, so it's a set function. It is a set function that gives you probabilities of events like x being in set A. Okay, so this set A usually, let's say, so this is a random variable. This is an event. Usually you take, for example, A to be an interval. Okay, so you, for example, consider A to be negative infinity to A. Okay, then the probability that x is in A is the probability that x is less than or equal to A. And this in this case has a name. This is usually called the CDF. The CDF of x. So, but formally, the distribution is just it's just a set function. A maps to P of A. Or sorry, the distribution of random variable x is this set function that maps events to these probabilities. Given any event, the distribution allows me to compute the probability that x lies in that event. One particular example is this interval. Okay. An alternative characterization is in terms of the densities for continuous variables. So for continuous RVs, an alternative description is via the probability density function, also known as written as PDF, the PDF. Okay, so what is a PDF?
Isn't it the lowercase f of x where you take the integral of it to find the probability density?
Right. It's something such that when you integrate it out over event A, this gives you the probability that x is in event A. So density is something that when you integrate out produces something of interest. So basically the area under it. So if I have a distribution like that, then the area, if this is A, this is B, if I integrate it, I get the area here. So this would be the probability that x is in, let's say, a to b, which would be the integral of f of x, let's say dx. So that's the f of x, the plot of f of x versus x. Okay, and so this in particular, this is the probability that I'm in an infinitesimal interval near. So this is just the probability that x is in, let's say, level x and x plus dx. If I perturb a little bit, x a little bit, I have a tiny interval there. So that would be like this. So I have a little tiny interval here, x and x plus dx. That's this probability. This would be that probability. So I integrate these little probabilities, and I get the probability of an event. Okay, so these are the ideas. And so if I specify this PDF, I have specified the distribution, because then I can compute all these probabilities. I know the PDF, I can integrate it out over any interval that you give me, and then I have the information. So now that we reviewed this, what is, how do you, for example, how can you define a standard normal? So how do we define?
Isn't it the
Yes,
function where it's the PDF is 1 over square root of 2 pi sigma e to the x minus mu something over sigma?
Yes, exactly. So we can specify its CDF or PDF. Specify its PDF, which, as both you and Farish mentioned, it's this it's PDF, which is that bell-shaped curve, right? So that's the standard normal, or the bell-shaped curve is basically this density, root 2 pi, if you want to write it, e to the negative x squared over 2. So that's the PDF of a standard normal. So it's centered at 0, and it has that shape, and then you can sort of plot it, and it would look like a bell-shaped curve. But many distributions look like a bell shape. It's not the only. So unfortunately, that's what people say. But let's say a t distribution is also bell-shaped. The Cauchy distribution is also bell-shaped. The key is how fast the tails go down, and the tails of this go down very fast, exponentially fast. Right. So how do we define? So this is the. So if x is normal 0, 1, this is the PDF. So how do we define, how do we define the general normal with mean, mu, and variance sigma squared? How do we define this distribution?
Isn't it 1 over 2 pi sigma and then e to the negative x minus mu squared over 2 sigma? Or,
Okay, say that again.
It's f of x is equal to 1 over sigma times square root of 2 pi.
Yes.
And then e to the negative quantity x minus mu over sigma squared all over 2.
Yeah, so that would be this. Or if I call this phi of x, this would be 1 over sigma phi of x minus mu divided by sigma. And the reason you can derive this by noting that, so if I call this, let's say, if I call this w, this is a random variable w. We can define, let's say we have W is normal 0, 1, if and only if, let's say, X, which is mu plus sigma times W, is normal with mean mu and variance sigma squared. Okay, so I can add this mu as a shift and scale with sigma, and I can get from a standard normal the general normal distribution. And if you know how to convert the how to transform a density once you transform a random. This is a transformation of a random variable. This is, as we'll see, an affine transformation. An affine transformation of a normal variable is another normal variable, and then you can compute the CDF. But in any case, so that's the CDF of a general normal distribution. So now the multivariate case. So for the multivariate case, we'll do the same. For the multivariate case, we have x1 up to xn. This is a vector. Say we have a random vector. We have a random vector x equal this. And to specify the distribution is again, so the distribution is specified. If we specify the density, so the density would be, in this case, so I would still have x, this is now a vector belonging to A, this is a subset of Rn. So any subset of Rn, I would have a density which when I integrate out, again, the same idea. I would get this. And so if I specify this CDF, sorry, this PDF, this is a multivariate PDF. So this would be like a multivariate integral, right? So over A, fx of basically x1 up to xn, dx1 up to dxn. It's a multiple integral. And as long as I specify that, I can take this multiple integral and then I get the probabilities, okay? And so this f x of little x, I would say, this is just the map. So maps Rn to R. Okay, so they're good, like it takes a vector and outputs a number, and then you integrate these. So for example, go ahead. Question? Any questions about this? Hello? No questions? I heard something. Okay, seems like noise. Right, so for example, let's say n is equal to 2. I have a vector x, which is x1 and x2. I could take the probability that x is in, let's say, negative infinity and a1 times negative infinity and a2. Okay, this is equivalent to saying the probability that x1 is less than or equal to a1 and x2 is less than or equal to a2. This would be integral negative infinity to a, let's say, 1, negative infinity to a2, f x of x1, x2, dx1, dx2. So it's this sort of set in, so this would be a1, this would be a2. I have to integrate over, I have a density and then I integrate it over this. And this is in general called the CDF, the joint CDF. So this would be f of, let's say, x1, x2. This is the joint CDF. Sometimes these things are called the joint distribution. Okay, so joint distribution. So this joint distribution has more information than the so-called marginal distribution. So if I know how to compute, has more information than marginal CDFs. So if I, for any single one of these random variables, x1 or x2, I have the CDF, I can compute the probability that, say, x1 is less than a1. Or I can compute the probability that x2 is less than a2. But to compute these joint probabilities, basically the probability of events that involve both statements about both random variables. So here I have an event that says this holds about x1 and this other thing holds about x2. To compute these, I need the joint distribution, or this joint PDF, or the distribution basically. But you just emphasize that this is the joint PDF, for example, to make sure that joint PDF. It's just a PDF, but joint is just for emphasis. Okay, this makes sense to people? Questions? Comments? Yes. Yes. Okay, so, well, no questions? So to define a multivariate normal distribution, I can just specify this PDF. It's a continuous distribution. And here you go. So that's here I'm using Y, but that's the density basically. I specify this joint PDF and joint PDF. So we say a random vector Y is a multivariate normal distribution, or for simplicity, I write MVN, with mean vector mu and a covariance matrix sigma if the PDF looks like this. So it's a multivariate function, and it just has this formula. Okay. And you can see this is the covariance matrix here, and this is the mean. So that's the mean vector. So you see it appears here, the covariance appears there, as well as in here. Okay, and so this notation here means, so this is just the determinant of sigma. Okay. So there's not much intuition here, except that this is gonna still be a bell-shaped curve, but it's gonna be a multivariate bell-shaped curve. So if I plot it in sort of, so let's say if you consider the case n equal to 2, this would be y1, y2, then I don't know if I can plot it or not. So the contours would be things like this. So it would have a shape like this. So all around. Right? So it's going to be like a thing that goes all the way, but it's like spherical all around. And so the center would be at mu, and the variances are determining so how, or the covariance matrix determines the shape, so how much it spreads across the space. And one thing, for example, to notice is that this reduces, reduces to, let's say, a star, where a star is this guy, for n equal to 1. So if you take n equal to 1, then sigma, the covariance matrix, is just going to be the variance, would be just the variance of Y, which is going to be sigma squared. And so sigma inverse is just going to be 1 over sigma squared. And the determinant of sigma would be, what is the determinant of a number?
It's just a number?
Yes, it's just itself. So you would have sigma squared here, and 1 over sigma squared here, and then this part is also, everything is a number, so it would be y minus mu 1 over sigma squared times y minus mu, which is analogous to y minus mu squared, or to sigma squared, case of n equal to 1. So it just reduces to that definition, but this is the general form. And so in general, so general NVM is complicated because sigma may not be diagonal. If its sigma was diagonal, then the inverse would be diagonal and things would simplify, but in general, you could have covariances. And so this thing here is not a simple object. It's a quadratic form, as we'll talk about later, but there's not much I can say. So the easiest way to visualize is to just plot it and see a bunch of shapes. And so the shape will be determined by sigma. But in any case, so in fact, you could say that any mu and sigma defines a multivariate normal distribution. So given any covariance matrix and any mu, I have a, let's say, unique multivariate normal distribution given by this joint CDF. So I can generate random variables from this distribution for any sigma and mu. So this is another fact for any covariance matrix sigma, let's say invertible at least, any invertible covariance matrix sigma, and any vector mu, the NVN is well defined. Okay, which may not be that much of a concern to you, but this is an interesting fact, that there is a normal distribution for every basically mean and covariance matrix, well defined. Okay, any question? Have you seen this formula before? Maybe in the chat you can respond.
Professor?
Yes.
Just a quick question. On
Yes.
top of the slide you wrote like reduces to star, could you please just go back up to see which one star was referring to?
Right, the star is just the univariate case, this guy.
Oh, okay. All right,
That's
thank you.
PDF, sorry, yes, no problem. Okay, other questions? Yes, one person has seen it. Other people have seen this formula? No, seen it, okay, no. Okay, so this is good to remember. In this course, we're not gonna use the PDF. So for example, it's useful if you want to compute probabilities, joint probabilities, you want to integrate it out. And let's say if you want to prove some of the results that we want to talk about, in this course, what we're going to use most is the numerous properties that this has. So the MVN has numerous properties. Most of them can be stated without, once you prove it, without reference to the PDF. And so this formula is there, but mostly unused in this course, mostly. So the things that I want to talk about are these properties, which are really useful, and we're going to repeatedly use them. The first property, the first important property, is that any affine transformation of a multivariate normal random vector is, again, a multivariate normal random vector. So if y has a multivariate normal distribution, if I apply an affine transformation to it, then the result is also going to have the multivariate normal distribution. So what is an affine transformation? An affine transformation is just any transformation that looks like this. So you take a matrix A and you take a constant B, you multiply y by A, and then add b. Okay. So mathematically, these things are called affine transformations. So the difference with a linear transformation, the difference. So if difference is b. So if b is 0, then it's also a linear transformation. Some people can call these affine transformations just linear transformations, but mathematicians sort of make a distinction between the case where b is 0, in which case it's called a linear transformation, and then b is non-zero, in which case it's called an affine transformation. So the general of b, so even if b is 0, it's still a affine transformation. But when b is non-zero, then it's not called a linear transformation. So linear transformations are a subset of affine transformation. In any case, the idea is that if I form this vector u as a y plus b, then this would have a multivariate distribution. It will have this density. The distribution will have this density. And because the multivariate normal distribution is completely specified by the mean and the covariance matrix, as you can see from the PDF here. I'm not proving this result, but let's say we know that the result is multivariate normal distribution. I just have to compute the mean and the covariance. And then if you go back to your previous, or our previous discussions, you can compute the mean and the covariance matrix of this. So the mean is just going to be A times mu plus B, and the covariance is just going to be A sigma A transpose. Okay, so why is that? So mu tilde is the expectation of u, which is the expectation of a y plus b. Okay, what can I do here? I want to compute the expectation of a times y plus b.
You just use the linearity of expectation. So it's just
Yes.
expectation of a, or it's a expectation y plus b.
Yeah, so b is constant comes out, and this is also going to be a times expectation of y, which we have seen before. It's another consequence of the linearity expectation. So this we have called mu. So you get this result that we have here. Mu tilde is a mu plus b. So how about the covariance? So this is going to be the covariance of u. So how do we compute this? Would be the covariance of a y plus b.
So then it's just the a squared covariance y.
Yes, but a is not. So this first, let's say this is equal to the covariance of ay. Why is that?
Because you just remove the b because it's a constant.
Yeah, because b is a constant shift, and covariance is invariant to shift to, let's say, constant shift. So if you add a constant vector to another vector, the covariance doesn't change. Because if you go back and recall, the covariance cares about the centered version of the random vector. So when you perform the centering, you just remove that shift. Okay, so now this would be the result that we use. So this is the result that when we use many times. So this is covariance of a. Y would be a covariance of y times a transpose. Okay, this we proved last time. And so you get this result because the covariance of y is sigma, so you'd get this other result. So this result is saying, so you can compute the covariance and mean. This is all saying that once you have that, the resulting vector also will have a multivariate normal distribution with this mean and this covariance. Okay, so this is a very important result, and basically allows you to construct new multivariate normal new random variables that are multivariate normally distributed from the old random variables that you know. So you can pass them through affine transformation, you get new multivariate normal distribution. So a particular example is this U, which is A transpose Y, where A is a vector. So A transpose Y, so what are the dimensions of U in this example? Dimension of U. Yeah, I see a lemma tree. That was probably for the previous question. So what is the dimension of U?
1.
1. I heard 1. Yes. So it's a scalar. But this is an example of this result with A being just A transpose and B being 0. Okay, A need not be, I mean, could be a row vector. That's another matrix. It's a matrix. So A transpose Y falls within this category. So A transpose Y is an affine transformation of A. So this result is saying that A transpose Y is going to have a multivariate normal distribution. It means A transpose mu. That's just this evaluated with capital A being A transpose and B being 0. And also the covariance, which is this guy with A replaced. So this is just A sigma A transpose. This is A mu, where A is just A transpose. Okay, so you apply that result with A being A transpose, and you get this interesting result. So because this is a univariate random variable, this is multivariate normal distribution here is just the usual univariate normal distribution. So this result is saying that A transpose Y has the usual univariate normal distribution. Another way of saying this, I mean, expressing this special case is that if I have a random vector Y, which has a multivariate normal distribution, if I take any linear combination of the elements, so this U, if you look at it carefully, it's a linear combination of the elements of Y. Okay, so U has the form summation AI, YI. If you look at the coordinates of Y and A. So if I take any linear combination of the elements of Y, the resulting random variable has this normal distribution with mean and the covariance that, or mean and the variance that you can compute. So this is going to be the variance of A transpose Y. This is the expectation of A transpose Y. Okay, any questions? Comments? I'll give you a few seconds to think about this and ask questions if you want.
Just a quick question where it says U equals sigma A1 AI YI. It's on top of it's like you wrote it on top of the word non-random.
No, that's not, yeah. So sigma here is also not, that's the summation. So let's do it here.
Oh yeah, I meant summation.
Right, so U is A transpose Y, and it's going to be the summation I from 1 to n, AI, YI.
Okay.
I didn't mean that it's related to that non-random state.
Yeah,
That's
and
just,
also, how did the A transpose become AI? Like just AI instead of the transpose?
no, you have to just remember so A is, should we do it here? So I'm going to do it on the other side. So go from the other side here. So A is just A1, A2 up to AN. Okay, and Y is Y1 up to YN. So A transpose Y is just going to be, sorry, let's do this here. So A transpose Y you take the transpose of this, you get A1, A2 up to AN times Y1, Y2 up to YN. Okay? So what is this product?
Just a bunch of AYs, like AI,
Yes.
A1, Y1 plus A2, Y2, so on until AN, YN.
Right. And then you can just write it compactly as I goes from 1 to N summation AI, YI.
Okay, thank
That's
you.
what I wrote here, right? Yeah, just you have to remember that A is a vector and A transpose is a row vector. And then Y is also another vector. So these are vectors. And so this is a vector multiplication. This has also another name. So if you remember, what is the name of this operation that we did, A transpose Y?
It's like I want to say orthogonal product or
Yeah, so it's not orthogonal, it's just the inner product.
inner product, there we go.
Yes, yes. They would be orthogonal if this is 0. This is, you can write as A inner product with Y. That's another method. Yes.
Okay.
So this is, yeah, good. So this is good to remember. So an inner product of a non-random vector A with a multivariate normal random vector produces a normal distribution. That's another way of saying. Okay. Good. Okay. So we work with these things a lot. So it's good to remember. A inner product with Y is equal to A transpose Y is equal to the summation. So this is how you get a general linear combination of, let's say, elements of Y by taking the inner product with another vector. Okay. Questions? I think that was a good question. Other question? I'll try to write it here. Equal to AY inner product. A and Y. Okay, good. No other questions? So I can't emphasize the importance of this enough, but we're gonna repeatedly use this. So keep this in mind. Let's move on to another property. So this is the second property, and it says marginal distributions of Y, which is multivariate normally distributed, are again multivariate normally distributed. So the marginal distributions of a multivariate normal distribution are again multivariate normal. So what do we mean by marginal distributions? Anyone can guess or have heard or knows. Go ahead.
The marginal is like, if it's like x equals x1, x2 is just like the distribution of x1 or the distribution of x2, so each component of Y?
Yes, yes, that's the basic idea. So for example, you have x is equal to x1, x2, that's a vector. So the distribution, when we say the distribution of this vector, we just mean the joint distribution, which is just any of these characterizations. So for example, the distribution are these probabilities, like a recipe for computing these probabilities, or can be equivalently stated in terms of the joint PDF. The marginals are just the distributions of each component. So yeah, so if I look at x1 itself, it has a distribution. And that would be a marginal distribution of this joint distribution. If I look at x2 itself, it's a random variable, it has a distribution. That would be a marginal distribution of this joint distribution. So the joint distribution contains more information than the marginal distributions. You can easily verify that if I have the joint distribution, I can get the marginal distributions as a byproduct, more or less for free. The opposite is not true. So if I have marginal distribution of x1 and marginal distribution of x2, I can't compute or construct the joint distribution unless I have additional information. So the joint distribution generally has more information. But here is saying that this result is saying that, for example, if x is multivariate normally distributed, then each of these individual marginals, marginal distribution x1 or marginal distribution x2, are again normally distributed, which in this case, because they're univariate, is just going to be usual univariate normal distribution. But this result is saying more. This result is also saying that, so if, say, if x is MVN. I'm abusing or notation, or it's like not notation, but I'm being a little bit sloppy. So I say X is multivariate normal. I mean the distribution is multivariate normal. Okay, but for simplicity, meaning that X has MVN distribution. But to avoid saying and writing this, just that X is in MVN, then X1 and X2 are normal variables. So individually, they are normal random variables. Okay, they have that PDF of it. Sorry, PDF of it. Normal variable. But this says more. This is saying that, for example, if X is equal to X1, X2, X3, not only individual coordinates are normal, but so X1 and X2 and X3 are normal random variables, but more is true. We can say that X1, X2 is also MVN. So this is another marginal. So marginals need not have a single coordinate. So if I restrict myself to these two coordinates, this piece is another random vector, and this piece will have a multivariate normal distribution. Okay. And also, for example, X1 or X2, X3 is also MVN. Okay, that's another piece here. So this guy is also MVN. If I take this out, that in itself is MVN. Even more interestingly, this piece here is also MVN. Okay, we should use a different color. So this piece here. So X1, X3, this is another marginal. This is also. Let's copy this. This is also copy and paste. Also MVN. This is also MVN. Okay, all these things are MVNs, or multivariate normal random variables. Okay, so this is the meaning of having a marginals being multivariate normal. So if you take pieces of the random vector that has a multivariate normal distribution, those pieces, if they form a vector, they have multivariate normal distribution. So the pieces need not be consecutive, so they don't have to follow each other. So you can take one piece from here. For example, another example, suppose, another example, sorry. So let's do this here. Another example. So if I have X, which is X1, X2, X3, X4, X5, this is a multivariate, it follows a multivariate normal distribution, let's say. Mean mu1, mu2, mu3, mu4, mu5. It's a little bit too much. Let's do this. 4 is enough. Okay. And then I have a covariance matrix sigma 1, 1, sigma 1, 2, sigma 1, 3, sigma 1, 4, sigma 2, 1. 2, 4, and so on. Sigma 3, 1, sigma 3, 2, 3, sigma 4, 1. Sigma 3, 2, sigma 3, 3, sigma 3, 4, sigma 4, 2, sigma 4, sigma 4. So that's the covariance matrix. This is the mean. Okay, so the idea is that if this is this vector has a multivariate normal distribution, then this other vector, which is as I take this piece, and this piece, okay, this is going to also have a multivariate normal distribution. So x1, x3, x4 is also going to have a normal distribution with a certain mean and a certain covariance matrix, and any other sort of combination of the elements. So anyone can tell me what the mean and the covariance it is will be.
The mean is going to be mu1, mu3, mu4.
Yes.
And covariance, I think I sort of remember this trick, but it's you take the first row and column, third row and column, and fourth row and column. You just
Yes.
exclude the second row and column.
Right. It's going to be basically the submatrix of the covariance matrix, which is indexed by these elements. So the indices of the elements are 1, 3, and 4. So I look at the submatrix on columns 1, 3, and 4, and also rows 1, 3, and 4. Yeah, so you can exclude the second row and column. So the submatrix would be this. So that would be the covariance matrix of this guy. Okay, so these elements go in there. Yeah, I should color them differently so that I don't have to write this, but let's say, yeah, that would be difficult. So it just goes the same. So this would be, so you get the idea. This would be just sigma 1, 1. This would be sigma 3, 3. This would be sigma 4, 4. Sigma 1, 3, sigma 1, 4, and so on. Okay, and you can easily verify that because the first element here has to be the variance of x1. And it's the variance of x1 also in this case. And the second element has to be the variance of x3, which is here in this matrix. And the third element has to be the variance of x4, which is this guy. And then this entry would be the variance of the covariance of x1 and x3, which in this matrix is going to be this element, and so on. Okay, so you get this. So now, so this is the result. The result says that if you pick a sub-vector, that's a marginal distribution. So an example of a marginal distribution. And similarly, you can do, for example, x1, let's say, and x4, and so on. All of these would have multivariate normal distribution with certain means and covariance matrices. So how can we show this? Let's say, given the result that so we have property 1. Can you use property 1 to actually prove this result? How do we prove this result? The one that I just wrote. So how can I show that? So I know that this x is multivariate normal. How can I show that this new vector x1, x3, x4 is multivariate normal?
So you can find a matrix A such that A times X equals to X1, X3, X4. You can apply lemma and get the result.
Great, yes. So if I can write this as an affine transformation of this other vector that I know, then I'm in business. And in fact, we just need a linear transformation if I can find a matrix. So what is the matrix? Is there a matrix that gives me this?
So by row it should be 1, 0, 0, 0.
Yes.
And 0, 0, 1, 0.
Yes, this chooses the third element.
And 0, 0, 0, 1.
Yes, so that's the A matrix. This is X. And the result is saying if I call this, let's say U, or let's say call this Y, then the result is saying that Y is going to have normal with mean A mu, and then A sigma A transpose. Okay, mu being this, that's mu, that is sigma. And you can verify that A times sigma A transpose gives you just the result that we talked about. It should give you this, this thing. Okay, so this, evaluate this using A, it should give you this. So this result is proved like that. Does that make sense? So it's a special case of an affine transformation. So you can always find, in fact, a linear transformation that maps a vector to a subset of its elements, another vector consisting of subset elements, and then you can use that result to drive the distribution. Okay, in general case is done like this. I encourage you to read this. There's some block approaches. So you can, for example, what this is doing is that I'm subdividing this vector into two pieces. Y1 and Y2 are not coordinates. So I should have written, for example, Y superscript 1. So this is bad notation. So what I'm saying is that if you subdivide, if you have a vector Y, and then you subdivide it into two blocks, so these could be consecutive or non-consecutive blocks, then the transformation that I need A is just going to be the identity and then zeros. And if you multiply this out, you get Y1. So this would be Y1, Y2, Y1 here. And then you can use the result. Yeah, I'll probably ask, or you can ask the TA to go through this if you want. This is just a general way of writing it. Okay, so for example, if I have, what that's saying is that it's easier when things are consecutive. So for example, if I have x1, x2, I can write this as 1, 0, 0, 0 times x1, x2, x3, x4, 0, 1, 0, 0. Okay, this is going to be identity 2, this part. And this is going to be 0 matrix. So I can write this as just identity 0 times x. Let's say x1 and x2, where x1 is this part and x2 is this part. And then this just turns out to be x1, which is just this guy. Then you can see that this is A, and then you can multiply. So A sigma A transpose is just going to go pick this subblock of sigma. Yeah, it's hard to verify, but just do it for yourself. This is the block matrix notation, which is a little bit advanced, but if you're comfortable with it, you don't have to write all the entries. Okay, probably don't shouldn't spend too much time on this. Did you get the general idea? Okay, if you're interested about the block notation, you can ask me or the TA for clarification later. Questions? All good? Okay, so let me just mention this last or two. We have two more properties. The third property is not going to be used in this course. I'm not going to use it, but it's very important and it's useful to remember. I just mentioned it in case you come across it later. We're just going to use a consequence of this. So I'm just going to mention it. So the conditional distributions of a multivariate normal random vector are also multivariate normally distributed. So not only the marginals are, the conditional distributions are. So a conditional distribution, you have to recall what conditioning means in probability. It's one of the most important operations in probability. And here we're saying if I divide, let's say, I should have used different notation here again. So I should have used, so this should be y superscript, y superscript. Just imagine these things for yourself. Y1 and Y2 are not coordinates. So I'm using this notation, general block notation. So Y1 and Y2 are blocks. So I divide this vector into two blocks, Y1 and Y2. A better notation would have been Y superscript 1 and 2. and then a condition on y2, which is saying, let's say I see y2, conditioning on y2, saying that I've seen this part. What can I say about the distribution of y1? That's the conditioning. So the idea is that if I see this part of the vector, y2, how does the distribution of the top part changes? And the distribution changes in general because conditioning affects the probabilities. And so this result is saying that the conditional distribution of y2, y1, given y2, condition of y2, is another normal distribution. So that's another normal distribution here, with a certain mean, which is given here, and a certain covariance matrix. And we know the mean is this formula. It's not, I can't say much about it. But the thing is that it depends on y2. Once a condition in y2, y2 becomes fixed, non-random, then the mean can depend on it, and it depends on it in general. The covariance is also going to generally depend on y2, but in this case, it turns out that the covariance is not dependent on y2. Okay, so this result I'm not going to prove, but that's just saying that distribution of y1, condition of y2 is like this. And note that if I set this equal to 0, sigma 1, 2, if sigma 1, 2 is 0, then this conditional mean, this is the conditional mean here. So this conditional mean is not going to depend on y2. So you can see this expression is going to be, so if you set this equal to 0, then this whole thing is 0. And so the mean, the conditional mean is going to be the same as the preconditioning mean, mu1. So we can just have mu1. And then the other term is also going to be simplified. So this is going to also be 0. Okay, if sigma 1, 2 is 0, this is going to be 0. So the condition mean is going to be, so covariance is going to be sigma 1. Okay, so this result is important because it shows that in this case, when this is 0, conditional distribution of y1 given y2 does not depend on y2. Okay, it's just the precondition. I mean, it's just the same as the marginal distribution of y1. And so, in other words, in this case, y1 and y2 are independent. That's one characterization of independence. And so this result shows that sigma 1, 2 being 0 means y1 and y2 are uncorrelated. And this result saying that in that case, they're independent. This happens only in a multivariate family, or at least not generally in multivariate normal family. So in multivariate normal family, uncorrelatedness is equivalent to independence. And because we're out of time, I'm just going to stop here. But this is an important topic, and I'm going to come back next time and elaborate more on that. Okay. Questions, comments? Any questions? Okay, if no questions, then let's stop. Okay. Thank you, guys. Don't forget to answer the poll. You're welcome, no problem. See you guys hopefully on next week. Okay. Okay. Thank you. Goodbye. Bye.